everyone. This week we're covering, the week of Memorial Day. First, we don't meet on Monday. We're not meeting on Monday. It's a holiday. Enjoy the long weekend. The week of Memorial Day, we are covering two chapters, chapters 4 and 5. And actually, there's comparatively little lecturing I need to do for these chapters. Most of our work will be application. There's a few things that I'll present, and then next week we will spend our time applying these concepts. The first thing we need, and then there's a couple of reasons to do this now, and the first one is to set the stage for chapters 4 and 5, and the second reason is to actually go back to chapter 3 and grab a piece that we sort of left on the cutting room floor at the time. Chapter 3 it starts our discussion of motion in multiple dimensions, often only two. Usually we can restrict ourselves to considering motion that occurs in a single plane, 2 dimensions. And there's a very particular kind of 2-dimensional motion that we haven't talked about yet, and that's motion in a uniform circle, motion in a circle of constant radius. So that's what I'd like to talk about first, and we'll start there and then proceed through chapters 4 and 5. And we might only have a couple segments today, or this week, because again, most of the legwork is not in lectures, but in applications, working through examples and problem solving and the like. So we'll start with motion in a circle. Let's, for simplicity, assume that it is counterclockwise motion in a circle of radius r. The object in question is some point object here that lives on the circumference of the circle. And its position at all times is given by a vector drawn from the center of the circle, which is the origin of my coordinate system, to the point on the circumference where the object is at the time. And we know that it has some horizontal and some vertical components, and we can write the vector position this way. But the thing is, we know how to describe circular positions. That's what the unit circle and sine and cosine were all about. We know that horizontal component is related to the hypotenuse by the angle that position vector makes with the positive x-axis. So I'll just call that theta for now. And we know that we can write this as magnitude of the hypotenuse times cosine of the angle theta in the I, plus the magnitude times the sine in the j direction, and that's also vector r. Cool. Now, there's, oh, I'm sorry, I meant to color code the rest of that. R sine theta j, according to what I've drawn here, with the plus sign. Okay, we could factor out the capital R if we wanted to. So that we're talking about cosine theta plus sine theta j hat. What's the magnitude of that thing in square brackets? Just out of curiosity. I'll do that over here. The magnitude of that thing in square brackets. We take the, let's see, so we take the square root of the horizontal piece squared plus the vertical piece squared, but sine squared plus cosine squared of the same angle is 1. So this has magnitude 1. So this is this thing in brackets is a vector with a magnitude of 1 unit. In other words, it is a unit vector. It's a unit vector in the direction of lowercase r, the position vector. So this thing in square brackets, I'm going to call this r hat. It's a unit vector, so it gets a hat, and it's in the direction r of the position. It's in the direction of vector r, the position vector. Cool. So far, so good. For the sake of argument, at least for now, let's suppose that this this motion in a circle occurs at the same speed. That every time capital T, let's say, one full circle every time capital T. Okay, so how fast are we going? If this is a car driving in this circle, what does the speedometer of the car say? Well, usually this is distance or displacement over time. Displacement doesn't do us a whole lot of good here. The displacement in a full circle is 0. But distance over time, the speed with which we're going in a circle, note that this has no vector arrow ornament. Distance over time in an amount of time, capital T, how far do we go? The circumference of the circle. Okay, cool. So that's a thing we know. As time passes, we move around the circle. So theta is a function of time. It starts, I guess, at theta equals 0 and proceeds so that it becomes 2 pi, and then, 4 pi, and then 6 pi, and then 8 pi, as we go circle after circle. We know that in an amount of time, capital T, we travel 2 pi radians. So in an amount of time, T over 2, we travel pi radians. What I'm looking for is theta as a function of time. I guess, okay, here we go. Theta increases at a constant rate all the way along because we take the speed we have and we average it over a circle. So there's no time at which we're going faster or slower than any other time. So theta should change accordingly. So, okay, theta of t when, so we've got a table here. When t is capital T, we've gone 2 pi. And when t is t over 2, we've gone pi. Can we, from this, figure out the function? I think so, because 2 points determine a line. If we let this be mx plus b, some kind of normal linear increase, then we should be able to use this information to figure out m and b. All right, so m would be the change in theta, 2 pi minus pi, divided by the change in t, so that's pi over t over 2. And then when we divide by t over 2, that denominator 2 flops upstairs. The intercept, all right, so wait. If theta is 2 pi, that should be t times the slope that we just calculated, plus the intercept, but the t's cancel and b is equal to 0. Okay, cool. So the function that represents theta of t is just 2 pi over t, that's the slope, times time. So this theta here, we could replace that equals r cosine 2 pi over t plus sine 2 pi over capital T j, close that bracket. The reason I wanted this, and I didn't tell you why at first, the reason I wanted this is because position, if I take a derivative with respect to time, I can talk about velocity. I just needed a function explicitly of time. Like I knew theta was changing, but I needed to figure out exactly how theta changes as time changes. And now we've got it. So now, I'm just gonna erase this part of the circle because I kind of need this part of the board. It's the trouble with only having this little whiteboard here. So now the velocity as a function of time is the time derivative of the position as a function of time. So we take the derivative of that with respect to time, r times. The derivative of cosine is negative sine. Trig functions keep their arguments when we take derivatives. Then we have to multiply by the derivative of that argument. And I hat is constant, so that just gets to stay there. Plus the derivative of sine is cosine. The argument times the derivative of the argument. Okay. Cool. Let's factor out the things that are constant. Equals, we've got r 2 pi over t sine pi over plus cosine pi. Does this expression out front look familiar at all? That's the magnitude of the velocity, which makes a lot of sense. We just calculated a velocity and its magnitude is exactly what we said it should be, circumference divided by time. This is sine and cosine. If we find its magnitude is going to be 1, but it's not the same direction. Here, the horizontal piece is negative instead of positive. So what direction is this? Well, let's find out. In the vector recitation this week, we found an angle by first finding a dot product and then using the other definition of dot product. So this, I'm going to call it, I don't know, Q for now. It's a vector. What is Q dot R hat? Now R hat we defined earlier, it's this guy. So this is, or this one if we want to write it with the 2 pi and the time and everything. So it's this x component and this x component. So that's negative sine 2 pi over capital T, T times cosine 2 pi over capital T, T. The product of the components plus the product of the y components, cosine 2 pi over capital T, T times sine 2 pi over capital T, T. That's a thing plus negative, the same thing. Okay, cool. If the dot product is 0, and the dot product is supposed to be magnitude times the cosine of the angle between them, that must mean the angle between them is 90 degrees. So this thing that I called Q is a directional indicator because it has a magnitude 1, perpendicular to R hat with a minus, so it's to the left and up because it's a negative x coordinate and or component and positive y component. So it's perpendicular to R and to the left and up, that's this way. That's tangent to the circle. Perpendicular to a radius, that's tangent to a circle, and it's indicating the direction that we're going around the circle counterclockwise. Wow, okay, so the velocity at all times must be perpendicular to a radius, which means tangent to the circle. Very cool. Okay. We know its magnitude, circumference divided by capital T, and its direction is perpendicular to a radius. If we can talk about the velocity, we can talk about the acceleration. taking into the derivative. This is constant. We can leave it out front here. R 2 pi over capital T. Here, the derivative of negative sine is negative cosine. The argument times the derivative of the argument. The derivative of cosine is negative sine. The argument times the derivative of the argument. Oops, but I forgot I and j. Okay. Let's factor out the piece that's constant. So that's r. We have 2 pi. We're going to be factoring out another one. So we're going to have 4 pi squared divided by t squared, because there's one here, and we're going to factor out another one, times, I'm going to factor out the minus sign as well, cosine 2 pi over capital T in the I plus sine 2 pi over capital T in the J. Wait another. Yeah. All right, let's start with this piece. This is this. It's the same expression. It's the same unit vector. There's a minus sign in front of it. So apparently, the acceleration has some magnitude, and we'll figure out what that, I mean, it is what it is, it's that. And the direction is opposite the position vector. Opposite the direction of the position vector. The acceleration must, apparently, be directed opposite, radially inward, instead of radially from the center out, like the position, radially inward. All times. Whoa, cool deal. Okay. And this is apparently just the required amount of the acceleration. If we're going to change all the time the direction of the velocity so that it's always tangent to the circle everywhere around, this is apparently what acceleration magnitude will accomplish that. If we cause an acceleration in this direction with this magnitude, we can create circular motion, which is pretty cool. This isn't the only way to write this circular motion acceleration magnitude. If we square 2 pi over t, we'll get 4 pi squared over t squared. We can't square this whole thing in the red cloud because then we'd end up with r squared, and we don't have r squared, we just have r. But we could get away with it if we write it as v squared, divide away the extra r, v squared would be just square everything. The 4, the pi squared, and the t squared we want. The r squared, I just want to take away one of those r's, and the way to get rid of it is by dividing. V squared over r opposite the radially outward direction, radially inward. Radially inward. There's the word we use for that, seeking the center. We write it in Greek centripetal. The radially inward acceleration is the centripetal acceleration. So we'll write it as either a rad for radial, or a sub c for centripetal, or circular if you like. V squared over r in the negative r direction. Cool. If we're going to speed up around the circle, that's the only other piece we got to talk about. If we're going to speed up, in other words, change the velocity in the direction of the velocity, in other words, keep the unit vector the same, but change the magnitude. The way to change the magnitude but not the direction of a velocity is to include an acceleration in the same direction. Well, we said that on Thursday, looking at acceleration components parallel and perpendicular to velocity. If there's an acceleration component perpendicular to the velocity like this, we can change the direction so that it always points in a circle. But that is exactly as much directional change as we need. We can't do anything else radially, because then we'll start to pull inward and the radius will decrease or increase if we change the radial acceleration away from this magnitude. The way to speed up is to apply some acceleration in the direction we're going. So overall, we might be talking about some kind of acceleration that has a radial component and a tangential component. The tangential component is the component in the direction of the velocity. So I'll write it this way. This is the acceleration component perpendicular to the velocity, and this is the acceleration component parallel to the velocity. And those are exactly the components that we talked about finding at the end of worksheet 3.1. We know the velocity direction. Let's find the acceleration parallel to and perpendicular to that. If the perpendicular component happens to have this magnitude and be radially inward, we're apparently talking about circular motion. We might be speeding up or slowing down. If a parallel turns out to be 0, then we're doing circle at constant speed. Okay. There's nothing here from chapter 4 or chapter 5. Not yet. The piece we're missing, or at least the question I have now, this acceleration is required in order to maintain circular motion. We are pretty sure we know what causes things to fall. You know, we talk about objects in free fall, and they move down in the down direction, and we are, we've talked about gravity being the reason why. What is that gravity is the cause, the source of falling motion? What is the source of circular motion? Where does this acceleration come from? Because it doesn't just happen. If I take an object and I swing my arm in a circle, if I let go of the marker, it stops moving in a circle. So it's not, it doesn't just happen. Where does that acceleration come from? That's chapter 4.